My name is iPoLS and I'm from Wolfgang Research Lab in University of Maryland. And we are interested in understanding the biophysical aspects of cell migration dynamics. Today I'm going to talk on the topic of nanotopography guides and direct cell migration and some of the underlying mechanisms that we have started to understand. In this slide you will see a neutrophil cell that is showing directed migration on a nanopattern surface. And what is interesting in this movie is the dynamic actin-like waves that are formed in the pseudophore front, and we think that these actin waves are very important in sensing the nanopattern surface while they are migrating. To give you a brief overview of how topography acts as a natural guidance cue, and some of us are very well aware of different guidance signals that a cell senses. To name a few are chemical, electrical, and also physical topography. These guidance signals, what they do is they rewire some of the internal cell's machineries and signaling proteins that allow these multiple pseudopods and redirects them to form a single stable lamellipodia. And this in turn allows the cell to direct migration in a particular direction. This kind of control direction and motion is very important from a physiological perspective. Let us see in this in vivo system in which the green cells, which are labeled as white blood cells, are responding to a focal tissue injury in mice. You should be able to appreciate the way that there is a rapid burst of sensing of the focal tissue injury by the neutrophil cells, and in turn they recruit more and more neutrophils from far away. And this we have understand from the point of chemotaxis, because the cells here in the focal tissue injury secrete some chemical factors that in turn communicate the far cells to migrate towards it. But now we also know that the neutrophils, while they migrate to this inflammation site, they also remodel the extracellular matrix in such a way such that the far cells can rewire themselves and also directionally migrate to the focal tissue injury. So what we are trying to do in the lab is trying to mimic this in vivo extracellular matrix environment. With the upcoming intravital second harmonic imaging, we have also, nowadays researchers have tried to understand the in vivo natural environment in living tissues. And this is showing here the living muscle tissue, and you can see that there are specific nanotopographic enriched highways that are present in vivo. And here you can see that the collagen fibers have formed this long rod-like shape and also some dot-like structures. So what we are doing now is trying to mimic this in vivo size scales of the aligned and non-aligned extracellular matrix environment by using various different kinds of nanotopography. Some of these are listed here, and trying to understand what cellular behavior one can see. As a first example, we have started to understand actin wave-like patterns on this nanotopographic environment and what are the other cues that the cell can sense. Towards this, the first initial study from our group showed that the adhesion-dependent endothelial amoeboid cells can directionally migrate along the nanotopography comprised of ridges. And as you can see that we have quantified the migration dynamics of the amoeboid cells and see that they can bidirectionally migrate, as shown here in the tracks. And not only this, we have used various different spacings between the ridges and found that there is a specific threshold of the spacing between the ridges for them to guide along the ridges. And that is around like 1.5 to 2 micron spaced ridges. Now that we know the optimized spaced ridges is about like 1.5 micron, we next wanted to find out what happens when we put adhesion-dependent immune cells like neutrophils on such nanoridges. So the left panel shows a DIC image of an optimized nanorid spacing of 1.5 micron, and the right panel shows you a confocal image or a movie of a neutrophil cell which is labeled with actin Y. What you can see is that there are consecutive and periodic bursts of quantified this extent of contact guidance, and we found that these propagation actin waves are along the ridges and they preferentially concentrate on the tops of the ridges. This is a space-time plot to show you the biased actin polymerization wave, and we have developed an actin polymerization tracking code to track each and every wave cluster unit at the pseudobot front. This is showing 3 different time points. Each time point is spaced between 2 seconds, and we have tracked each and every cluster unit by an optical flow algorithm. Panel C shows you the histogram of the average actin wave speed where the cells are running on such ridges, which is around 20 to 30 micron per minute. Panel D shows the persistence of a single actin wave cluster on a single ridge, which is around of the order of 5 to 10 seconds. We then fixed and immunostain these cells which are running on the ridges, and like actin microfilaments, we also find these microtubules are also aligned along the ridges, and we think that this is indeed essential for guiding the neutrophils along the ridges. We went ahead and analyzed several of these cell migration tracks of neutrophils on the ridge surface and compared it with flat surface similarly coated with fibronectin ECM. And what we see that on flat surface, the cells are showing random motion with no sense of directionality as shown in this polar plot. However, when we place the cells on these nano ridges, we find that suddenly the cell shows directionality and they are bidirectionally guided. Although their speed is not very different, but their persistence definitely changes when we place them on the ridges. We went further and looked at the shape dynamics of neutrophils while they are on the ridges, and this shows the overall shape with respect to time on the ridge. And you can see this color bar indicates the time between the frames and how they are evolving with time. And the final shape dynamics is shown here in black with vector codes, and the initial shape is in gray. And this shows a single shape dynamic at a single time point where you can see the boundary curvature of the entire boundary of the cell. And when we plot them in a space-time plot, what we find is that the positive boundary traverses from the front to the back of the cells in an oscillatory fashion, and this is very true because the cells are moving in a stable pseudobot and are contracting and retracting. Next, we went ahead to find another addition-dependent epithelial MCF10A migration on these ridges, and the left panel shows a flat surface coated with collagen 4, and the right panel shows a nano ridge spaced 1.5 micron in between, and they are also coated with collagen 4. When we place the MCF10A cells on the same way, and this is about a 10-hour-long movie, you can see the cells are stretched, elongated, and they bidirectionally guided along the ridges as compared to the flat surface. We also wanted to find out how they look like, and when we looked at their tracks of running cells, the MCF10As again shows bidirectionally guided on the nano ridges compared to the flat surface where they are randomly migrating cells. And we also find no difference in the speed, overall speed in both flat and the nano ridge, but definitely there is a difference in the durational persistence. When we stain the MCF10A cells on the nano ridges, we find both actin filaments and microtubules are aligned along the nano ridge topography. And this is a snapshot of the 3D convolution of this several Z slices, and what you can appreciate that the cell is grasping on the nano ridge with 2 pseudobot fronts, and that's allowing the cell to bidirectionally guide along the ridges. So what is the significance of this entire study? What we are trying to think in immune cells is the pathways that might affect this overall actin cytoskeletal dynamics and nuclear shape might be able to determine some of the pathogenic activation pathways of neutrophils in physiological conditions, for example, rheumatoid arthritis. What we now think and hypothesize that these topographies can also act as a physical diagnostic marker to characterize different signaling pathways and phenotypes observed in neutrophils from healthy and pathophysiological individuals. Now we are asking the question, can altering the physical texture can affect actin cytoskeletal dynamics, and whether that can alter in turn the potential pathogenic properties of immune cells like activation, migration, and recruitment. We have just started work in cancer cells, and we are trying to use the nanotopography and trying to say whether we can control the direction and persistence of malignant cells by remodeling the entire cytoskeletal dynamics. With this, I would like to thank our LOCERT group team who have given their inputs for this project, and also my co-authors, Shayu, Rachel, who will be presenting their poster in detail on this topic tomorrow, Matt and Shayu makes this nice nanotopographic surfaces that we use for our studies, and Tiffany, Awa, and Song that has also contributed for this study. And also the past students, John Coogan and Megan Driscoll, they have optimized all this algorithm and customized scripts to run and quantify the same migrations. With this, I would like to thank the entire audience, and if there are any questions, I would be happy to answer.
So you mentioned in passing that you think microtubules are important for persistence, and there's a paper, which I'm sure you know, by Yuli Wang's group, that argues that microtubules also are important for persistence. Have you checked that by doing microtubule inhibitors in your cells to verify that?
Yes, actually this is very initial study, so I haven't given the results yet. But yes, we have tried to use nocodazole inhibitor, and that disrupts the contact guidance to a great extent. So that I have used in neutrophils and not in cancer cells yet.
Oh, so very interesting with the 1D case. I think it would be interesting if you did a torus, you could end up getting some very interesting collecting motions or rotations. But more generally, a lot of people worry about 2D to 3D, and yet you're going back to 1D. So what do you think you learned from the 1D motion case that is applicable to 2 and 3-dimensional in vivo systems?
Yeah, a very good question. Like it's always a dilemma, like whether we should do it 1D, 2D, or 3D. But if you talk to people who are doing a lot of intravital imaging studies in cancer cells, they are now going back to 1D, and that's the relevance because they find that there are one-dimensional, tracks, collagen fibers where the cells follow each other, and that's important in cell migration in tumor cells. So that's like going a step behind from 3D to 1D and skipping the 2D, I guess. But coming back to your first question about the round structures, so we have also tried to build concentric ring-like nanotopographic structures, and there is some chirality that is seen by the cells, and they can see the left and right-handed, and that microtubules are indeed the players in that.
I wonder, have you looked at the height of your topographic spacings? You looked at the lateral spacing. What happens with height? Do you see the same kind of transition?
Yes, so we have played around with height of about 400 nanometer to about like 2 micron, and we see maximum guidance between 1 to 2 micron, but below 1 micron it's not that good. So 2 micron gives the best guidance, 1 to 2. We haven't really reached beyond 2 micron, and it also depends on the cell type. For example, dictyostelium, they are very amoeboid and they do not really adhere to the matrix, so they really do not care about the height. But neutrophil cells, and I'm sure the epithelial cells also, they really depend on the height of the ridge.
Let's have the last question.
So I was interested in the motion of cells on the flat surface. Some of them do look like they're showing directed motion. If you look at the arrangements of the microtubules and the actin in these cells, do they have similar alignment features as those on the structural kind of pattern surfaces, or is this a general feature of their motion, or is this specifically responding to the surface?
So we did do a lot of immunostainings on the flat surface, and yeah, of course, when the cells are directed, which is like 1 or 2%, the microtubules they are also aligned in the same direction of motion. So I would say that the microtubule alignment is definitely related to the cell migration, but they align along the fibers. So wherever the fibers are located in a flat surface, they will be aligned accordingly.